All right. So first problem, if you remember, was this frame structure determinate, where you were asked to use the Castigliano's theorem to find the horizontal deflection of C. And as I mentioned in class also, the calculations end up being extremely similar to, well, exactly the same as the virtual work method, but you need to use a different approach. So you have the actual system, bending moment diagram should look like that, and which should immediately tell you that there is no bending moment here. So that leg should remain straight, but it does not mean that that leg should remain vertical. Uh, that leg should remain straight, and there would have this frame would have a horizontal deflection to the right because of that. And to find that deflection, you have the additional system where you apply an additional PI load here, find the bending moment diagrams for that portion, and you need to take derivatives of the bending moment diagram with respect to that PI. And after that point, it's just an integration of two terms, and you should have ended up with 32 over EI as the displacement. So I think this was relatively straightforward. If you did not make a calculation mistake or a mistake in drawing the bending moment diagrams, you should have gotten the correct answer. Any questions about this problem? No? Okay. Um, this problem was an indeterminate truss with a degree of indeterminacy of 1. And what I asked you was that find the internal forces in these three members. So you should have used, again, the force method where you cut one member. And this is an important point that I'll emphasize again. I saw that some of you actually, instead of just cutting it, completely removed that member, which is incorrect. You're not removing a member, you're simply cutting the member and trying to measure the displacement, either overlap or separation at the cut. And in order to do that, you would then typically be using the virtual work method. You find internal, you apply unit loads at the tip of the cut, and you find the internal forces, virtual internal forces times real displacements. What you get was 125 over 3 AE. And you find the flexibility at the cut. So this was a common mistake that I saw, that in the flexibility, some students did not account for the flexibility of the cut member itself. So that's why it's important not to remove the member, but to just make a cut in that member. Having this term here is extremely important. If you don't have this term, then you end up actually getting that this member does not take any force. So that was a common mistake that I saw. And finally, the results that you should have seen was 4.19 kips in the straight member and 1.5 compression, everything in compression on the diagonal members. Symmetric half of the problem was also something that you should have been able to see from the deformation, of this truss. You should be able to see that D would go vertically down, right? In order for D to go vertically down, I would need a vertical roller here. I would also need to half the load. Instead of 6, it should be 3. I would also need to half the area of cross section of this member. So AE over 2 is what we should have here. These two remain pins. There should not be any roller here. With truss members, it's always a connection as a if it's a single truss member, it's always a connection as a pin. Okay. Some of you I saw also tried to actually first solve part B and then try to calculate the internal forces, which is also okay. If you do it correctly, you'll get exactly the same result. And hopefully you are seeing that with your current homework 7, whether you solve the entire problem or the symmetric half of the problem, you'll get exactly the same result. And finally, for the composite beam problem, the question said, find the internal force in AC. I did not actually ask you for the vertical displacement, so there's something extra in the solutions, but you can ignore that. For this, again, if you cut that member AC, then you can find the bending moment diagram of this beam. minus 10x. Apply 1 and 1 here. That bending moment diagram would be 5 over 13x. And at that point, you can find the displacement at the cut using virtual work. Same thing for the flexibility, and you need to, of course, account for the axial deformation in this member for the flexibility, and then finally enforce compatibility to get 12.6 compression in that member. Okay. So please take a look at the solutions. They're posted up on the Blackboard webpage. And if you have any questions, let me know. Or if you find any totaling errors or grading discrepancies, let me know immediately. Okay. Any questions on the quiz before we jump back into the stiffness method? I think most of you did very well on the quiz. I think aside from small calculation errors, I did not see too many of you making big conceptual mistakes. So that's good. Okay. All right. So let's jump back into the stiffness method that we started last time. And maybe even before I do that, let me ask you, how many of you have started homework 7? Okay, a good number of you. That's great. And anybody having trouble with getting the MATLAB code working? I think for problem 1 and 2 on homework 7, it's simply writing a new input file for the given trusses and running the code that I've given you. For problems 3 and 4, you would have to make changes to the code. And actually for problem 4, where I ask you to solve a 3-dimensional truss, I've posted a partial set of codes for 3D trusses, which is very similar to the 2D trusses, the code that you already have. So if you derive through the equations, you should not have too much trouble with that. Another quick point I'll make about some questions that were also posted on the discussion forum. In problem 1 and 2, I believe, well, actually only in problem 1, I'm asking you for A, N, and F matrices for those trusses, right? And if you look at, so maybe I should open that first. Okay, need internet connection here. So cancel. Oh, okay. So statically determinate truss 2D is the main file that you should be using. And hopefully it's open now. So yeah, in this is the main file that you would use for problem 1, because problem 1 is all determinate trusses. For problem 2 on homework 7, that's all indeterminate trusses. So you would use the flexibility or the force method for that. Here, if you run this code, you will see that within this call, the solve truss 2D call, the way to actually obtain A, N, and F matrices, the best way would be to use the MATLAB debugger. And once again, if you haven't used it before, or if you didn't follow what we did in the previous lectures, the best way to do that would be to place a breakpoint here, click on that run icon, and it'll ask you for an input file. So I'll pick one of the sample input files, which are also up on Blackboard. Open, and this is just plotting that particular truss. And once MATLAB reaches this line number 28, for example, so for solve truss 2D, it stops there for me to take further action, or for you to take further action. What I would do is then say step in, which is, I think, one of these icons. So step in is what you want to click on, which means I'm asking MATLAB to go into this function. So when I go into that function, let's click that. So I've gone into that function. I have the nodes of the truss, I have elements of the truss, I have boundary conditions, support conditions of that truss, and loads for that truss. What I want as output from there is element forces, support reactions, matrix, the A matrix, and the RHS, which is the F vector. So if you what I would like you all to be able to do is to go through this code by taking one step at a time. So once you are within this subroutine or once you're within this function, click on this step button. So this is step F10. What this means is that I'm going to be executing one line at a time, and as I execute them, I can see what are the values of these matrices and right-hand side vectors. These values would also be stored in the MATLAB workspace. So if you click on this button up here, it shows you the workspace for each one of those programs. There is this base workspace, there is the workspace or the memory for the main program, there's the memory for the solve truss 2D, the function that we are just talking about. So within this solve truss 2D, there are these variables that are already created. Once you reach the end of this function, so I'll put a breakpoint near the end of this function here, and I'll simply say continue to that point. So MATLAB will just execute all of those statements, and of course it goes very fast. It's already done with all that. You can see that the value of the matrix has completely been calculated, which is also stored in this variable matrix. So if I click on that and say open, then it opens up that matrix and it shows me all those values. What you can do is either open up these values, copy and paste it to a separate text file, and compare it to your handwritten derivation of the A matrix, and of course they should match. And you can do the same thing for the RHS, and lastly for the solution. The solution would be the n vector, right? A n is equal to f is what this code is really solving, and that's what I've asked you to obtain from the code and compare it with your hand calculations. Make sense? Okay. So if you have more questions, I'll be happy to take them on the discussion forum, or you can drop by my office hours or Dr. Liu's office hours. And if you're struggling with it, I'd suggest start early, because sometimes it takes a little while to remember what you might have learned long back in your freshman or sophomore year, right? Okay, all right. So with that, we'll jump back to the stiffness method. So very quick recap of what we talked about last time. I told you that for the stiffness method, the idea is that we'll break up a structure. Any structure, could be a truss, frame, composite structure, whatever. But for now, we'll look at only truss problems. We'll break up any structure into its component elements. So there are these 7 elements in this truss and 5 nodes. And the entire idea is that if I can somehow express the force displacement relationship of each and every element in the truss. So if there are 7 elements, if I can somehow express that for a particular member M, which is connected to nodes I and J, then if I'm able to find out what would be the force in that member if node I displaces by some amount delta Ix, delta Iy, and node J displaces by delta Jx and delta Jy, then I should be able to figure out what that internal force would be, right? So if I can figure out that part, the force displacement relationship for one element, then I can figure that out for all the elements. And finally, I should be able to combine all of these elements together to come up with a force displacement relationship for the entire structure. And that is what we will use to find the displacements of each and every node in the structure. That's the overall idea of the stiffness method. And as I pointed out, it doesn't matter whether the truss or the structure is determinate or indeterminate. Exactly the same method will work for both. Okay. So last time what we did was we described the structure with nodes, member connectivities, and we assigned degrees of freedom to each one of those nodes. Since it's a two-dimensional truss, each node has 2 degrees of freedom. And we said that if I am looking at a general node I, then the degrees of freedom associated with that node would be 2i minus 1 and 2i, right? So for 4, it's 7 and 8. And further, for example, in this truss, if there are 5 nodes, so there are 10 total degrees of freedom. And out of those 10 degrees of freedom, some of the degrees of freedom are free to move. Those are really what we want to find. Those are the unknown displacements that we want to find, free degrees of freedom. The others are specified degrees of freedom, which in this case is 0. So I have no displacement at 1 and 2. I have no displacement in 5. I have no displacement in 9 and 10. So those are specified degrees of freedom. I already know the displacement at those points. So in general, this will be true for any structure. Some degrees of freedom will be known, will be given, specified. Others would be what we want to find. So we'll see how we can construct the force displacement relationship for a big truss structure using the force displacement relationships for each and every individual element. And last time I also told you that in order to be able to combine the force displacement relationships for different elements together, we need one, a global coordinate system, and another, a local coordinate system. And at this point is extremely important to know which coordinate system you are working with. So initially, we work with the local coordinate system. And then we figure out a way to convert those vectors to a global coordinate system. And last time I showed you that the way to convert those vectors is using this transformation formula. And really, this is not a formula that you need to memorize. It's something that you can derive, again, very quickly. If you have a vector is an abstract quantity which does not depend upon whether I'm choosing xy or x prime y prime. A vector is a vector, is a physical quantity. It does not depend upon my coordinate system. So as I pointed out last time, if I have a vector from that corner of the room to that corner of the room, I can express the components of that vector in any coordinate system. So the same vector expressed in the global coordinate system is Vx, Vy. The same vector expressed in a local coordinate system is Vx prime, Vy prime. And using simple geometry, we came up with this relationship between the global and the local components. And I told you that this relationship is much more easily expressed in the form of a matrix. So using this matrix, which is really just cosine, minus sine, sine, and cosine, right? So using this transformation matrix, I can convert a local components to global. And using the inverse of that, which actually happens to be the transpose of that matrix, what are these types of matrices called? Matrices for which the inverse is equal to the transpose, orthogonal matrices. So since these transformation matrices are orthogonal, you can simply take the transpose of that matrix, multiply it with the global components to get the local components. So this is a good way with T and T transpose matrices to go between two sets of components, to go from local to global and back from global to local. So this is something that you should absolutely understand. And then finally, last time we looked at this local the local force and displacement relationship in the local coordinate system. Okay. What we did was we said that the force in a truss member would be proportional to the displacement, the net total displacement of the member. So that's delta L. We expressed delta L as delta Jx prime minus delta Ix prime, right? Delta Jx prime minus delta Ix prime. That would be the change in length of the member when it goes from the undeformed black configuration to the deformed blue configuration. And using that, I can immediately calculate what would be the force in the member. So force would be just AE over L times that delta L. And using that, what we did was we came up with this 4x4 matrix system of equations to represent that relationship, that force displacement relationship. Now, let me explain this carefully. What we are doing is we are saying that the forces at node I in the x prime direction and in the y prime direction, similarly forces at node J in the x prime direction and the y prime direction, and hopefully you should be able to see that if I can fit it into one page. But at node I have something in the x prime directions and 0 in the y prime direction, right? In the x prime direction, I have minus Fm. That's why we have a minus Fm and 0 for forces at node I. Forces at node J, it's plus Fm and 0. And clearly, you can see that plus Fm is in the direction of x prime. There's nothing in the y prime direction. So these are the 4 forces for the two nodes I and J that we are trying to find. And simply by using this equation, we expressed those forces at nodes I and J in terms of the displacements at node I and J. So as I pointed out, only the x prime displacements affect. So we had +1, -1, -1, +1, and the rest of the two rows are 0. So essentially we are saying that we have essentially 4 equations here that are describing the forces at node I and node J in the x prime and the y prime directions. And if you look closely at it, the row number one represents this force, which is in the minus x prime direction, and row number 3 is the exact same equation, but for this force in the positive x prime direction. Okay, so it's not like we have come up with 4 new force displacement relationships for a truss element. There is only one force displacement relationship really, and that is that force is equal to AE over L times delta L. Just by writing that equation in these two different forms, we have been able to correlate the forces at node I and node J in terms of the displacements at node I and J. Okay, and that was where we had reached about last time. So keep in mind, no matter what truss element you have, no matter which orientation that truss member has, the local force displacement relationship will always be given by this. Why? Because this is the force displacement relationship in the local coordinate system. The local coordinate system follows that truss element. So if the truss element is horizontal, the x prime and y prime coordinates are aligned along the truss member. If it's inclined, x prime and y prime go along with it. No matter which way it's inclined, the local coordinate system is always aligned along that. And therefore, this relationship pretty much captures the force displacement relationship of a truss member, which is just simply as simple as F is equal to AE over L times delta L. Okay. All right. So a shorthand way of expressing this relationship is basically just combining this 4x1 into a QM prime. Wherever I have a prime, that prime denotes local coordinate system. Okay. So forces in the local coordinate system, which actually consist of 2 parts, Qi prime, Qj prime, that's what Qm is. And they are equal to this 4x4 matrix, which I'm calling Km prime. Again, Km prime because this is local coordinate system, and then delta M prime, these are displacements in the local coordinate system. So this is just a shorthand way of writing this big 4x4 relationship. And this will come in real handy when we want to assemble all of these force displacement relationships for all the elements. Okay. All right. So let me ask you this. If I have a truss, a relatively large truss with elements in that truss oriented in all different directions, some are vertical, some are horizontal, some are inclined at 45, some are inclined at 30, and so on, then using the formula or using that 4x4 equation on the previous page, this equation, I can figure out I can figure out the local force displacement relationship for each and every one of those truss elements. Can I directly add those components together? So for example, if I have two truss elements, they meet at a node. For truss element A and truss element B, I want to find out what would be the forces these elements apply on the node. So can I add forces that I have in x, y prime, x prime, y prime components for A and x prime, y prime components for B? We can't. There are two different coordinate systems. So what we do need is a common coordinate system for all truss elements. And that common coordinate system is the global coordinate system, this x, y. So what we need to do next is to convert that 4x4 system of equations to a different 4x4 system of equations that is expressed in terms of global coordinates. Once I have forces and displacements for all elements in global coordinate systems, I can simply add them all together. Okay, so that's what we're going to try to do. So let me ask you this. I have QM prime, which happens to be a 2x1 and another 2x1, which is basically QI prime and QJ prime. It's a 4x1 vector made out of two 2x1 vectors. If I want to convert this vector from local coordinate systems, so I have a vector FM which points along x prime. If I want to convert that FM vector from components in xy prime, y prime to xy, how can I do that? Is there a way for me to convert this components, local components, to global components? How would we do that? Andrew? Right, that transformation matrix, right? So we'd go back to this guy. I have local components. I want to convert them to global components. So what I want to do is to multiply by cosine, minus sine, sine, and cosine, the transformation matrix. So that's exactly what we'll do here. We'll say that I need to multiply with cosine, minus sine, sine, and cosine. That's the transformation matrix. And the forces at I do not depend on forces at J. So the other four numbers here would be 0. Similarly, if I look at the force components at J, then these two force components can be evaluated from these two force components, again by using exactly the same transformation matrix, cosine, minus sine, sine, and cosine. And since it does not depend upon I, these four numbers would be 0. Right? So simply by using this transformation matrix, I have been able to convert this Fm, which is pointing along x prime, to two components, Fix and Fiy, which would be the components in the x and the y coordinate system. Once I have these guys, once I have the components for the forces in the global coordinate system, I can add all of these forces from all of the elements very easily, directly, right? So that's exactly what we're going to do. And yet again, a short way of expressing this is a transformation matrix, this is a 0 matrix, this 0 matrix, and this is a transformation matrix. So this guy was T, this is 0, and 0 and T. So all that we have done here is come up with a way to convert local force vectors to global force vectors. And note that there is prime here because that's in local and no prime here because that's global. Um, so in doing this, what we have really done is we have converted the left-hand side. We have converted the left-hand side of this force displacement relationship to global coordinate system. What we also need to do is to convert the displacements to global coordinate systems, because these are also again local coordinate system. So what we would need to do there is to write it as t 0 0 t, and I'll substitute qm prime from the previous slide. You should be able to see is km prime times delta m prime. So I'll write that here, km prime times delta m prime. And what I want to do is to convert this from the local coordinate system to again the global coordinate system. So what should I do in order to do that? To convert this from local to global, again the transformation matrix, right? So for this, I should have T transpose. Right, so what we would need is this relationship. I have primes. I can replace that with T transpose times global displacements. Okay, so I have local displacements. I'll replace them with T prime time or T transpose times global displacements. So I will write that as T 0 0 and T times km prime and T transpose 0 0 T transpose times delta I and delta J. And maybe just to make it even more clear, I'll replace this delta m prime with the actual local displacements, which are delta I prime, delta J prime. So I hope this is making sense. All I did going from here to this point is substituting for qm prime. Substituting for qm prime, I get km prime times delta m prime, right? And then I substitute for delta m prime as T transpose times delta I and delta J. So all we have done is we've converted this local force displacement relationship, we've converted that to a global force displacement relationship now. Because if you look at this entire matrix, let me ask you this. What's the size of this km prime? What's the size of this km prime matrix? Four cross four. And size of these this transformation matrix, each one of them is 2 cross 2, 2 cross 2, and 2 cross 2 and 2 cross 2. So 4 cross 4 multiplied by a 4 cross 4 multiplied by a 4 cross 4 gives me a total another 4 cross 4 matrix, right? That 4 cross 4 matrix is what I'm going to call Km global. So that entire matrix, which is a T times Km prime times T, that becomes a global stiffness matrix. And this is a common theme that you'll see for vector transformations and matrix transformations. For vector transformations, if you want to transform a vector from local to global, you multiply by T or transformation matrix times that vector gives you global. If you want to transform a matrix, from local to global, you multiply that, pre-multiply that with T, and post-multiply that with T transpose. So this is something that that happens very often for transformation of vectors and matrices. Now, using this relationship, I have forces in global components, displacements in global components, and stiffness terms in global components. So I have another 4x4 relationship, which is the global force displacement relationship. Simply by using geometry, simply by using transformation rules to go from x prime, y prime to xy, we have converted this local force displacement relationship to this global force displacement relationship. Let me ask you a question here. Um, if I have a truss element um, in the horizontal orientation, I'm telling you what the A, E, and L values for this truss element are. Then using those A, E, and L values, you can express the local force displacement relationships for that element. Right? That would be this relationship, exactly this relationship. Right? Now, instead of horizontal, if it is oriented vertical, would this relationship change? Would this relationship change? No, it doesn't, because that relationship is expressed in the local coordinate system. Like I said, it in the local coordinate system is always oriented along the member. If it's horizontal, x, y prime are oriented like this. If it's vertical, x prime, y prime are oriented like that. So this relationship will not change no matter what the orientation of the truss element is. But what about the global force displacement relationship? If the element is oriented horizontal in the horizontal direction versus the vertical direction, would it be different or would it be the same? Different, because we are modifying that relationship with this T and T transpose matrices. In the local coordinate system, that matrix is extremely simple: +1, -1, -1, +1. Everything else is 0 and multiplied with AE over L. And if I take that matrix and multiply it with, or pre-multiply it with a transformation matrix that looks like this: cosine, sine, and cosine and minus sine, and so on. This is this transformation matrix, and if I take the same transformation matrix to take a transpose of that and post multiply it, that will give me a new 4x4 matrix, which will be very different from the local matrix, right? So so keep in mind that even if I have two elements exactly the same size, E, A, E, and L, one is horizontal, one is vertical, one is inclined, all three of them will have the exact same local force displacement relationships, and they will have different global force displacement relationships. But once we have these global force displacement relationships, we can simply add them together. And this adding them together is a process which is called assembly of elements. So what we want to do really here is to make sure that for a truss structure like this, once we have the global force displacement relationships for all of these elements, we want to make sure that sum of forces at all of these nodes is 0. That's equilibrium, right? So so what we'll do is we'll write these equilibrium equations by using these force displacement relationships. And in order to do that, I'm going to go back to this slide and point out something else. I have this member M, which is connected to nodes I and node J. Given the displacements in the X and the Y directions, I can tell you what the force at these two ends would be. The force on the actual node that this element exerts is equal and opposite to this. Is that right? Newton's third law. If the member is in tension and the force Fm on node I is pointing in the negative x prime direction, it will be pointing in the positive x prime direction on node I. Similarly, on node J, if the force Fm is here pointing in the positive x prime, it would be pointing in the negative x prime on the actual node. Why is this important? Because I want to sum forces on the nodes, not on the elements. So if I have the forces Qi and Qj on the actual element, the forces on the corresponding nodes would be minus of that. Okay, so let's keep that in mind as we try to sum up all the forces, for example, for this truss. So let's take a look at how we would do that. For element A, it is connected to nodes 1 and 2. So the forces would be in the global coordinates, it would be QA1 and QA2. And there would be a minus sign. Let me write that in red actually. The minus sign because force on node is negative of the force in the elements, right? So again, what all that I have done here is I've taken element A and I'm adding the contribution of element A to nodes 1 and 2. This is element A. It is going to apply forces to nodes 1 and 2. So that those forces would be QA1 and QA2. These two things are exactly what we had on the previous page, right here. Q1 and Q2. This is Q1 and Q2 for a particular element. And similarly for element B, it would be connected to nodes 1 and 3. So I would add that to QB1 and QB3. Okay, what would be the contribution of element C to this equation? Contribution of element C is connected to 2 and 3. So all I need to do is to add QC2 and QC3. Similarly, element D is connected to 2 and 4. So we have plus QD2 and QD4. E is connected to 2 and 5. So we have QE2 and QE5. These are all 4 cross 1 force vectors which have 2 cross 1 components within them. Okay. what would be the contribution for element F? Three and four. So it's connected to 3 and 4, and QF3, QF4, and finally for element G, we have QF4 and 5. So QG4 and QG5. Using this, what I've done is summed up all of the forces on all of these nodes from the contribution for all of the elements. We do still have external forces 10, and after that I'm done. Just give me maybe 30 more seconds. So at node 2, I have this force in the x direction 10. I'll add that. So node 2 is right here. In the x direction, so 10 and 0, those are given. And finally at node 4, I have vertical direction -10. So at node 4, I have 0 and -10, and everything else is either 0 or unknown. So at 1, x and y are the unknown reactions that I'm trying to find. So I'll write those as question marks because I don't know what those are. At node 2, I've already said 10 and 0. At node 3, I have an unknown reaction in 3x. So I'll write 3x, and 3y is 0. And finally, at node 5, I have two unknown reactions, 5x and 5y. So at this point, I have an equilibrium equation for that entire truss. All we did was sum up the local force displacement relationships, and we get a big system of equilibrium equations for the entire truss. And next time, what we'll do is try to find these unknowns. All right, so let me stop here. I'll see you on Friday.